Okay, so just finishing off this example here, I want to just show you the graph on Desmos. You can see it looks very similar to what we had, just dipping below slightly here. And if you zoom out, I've added in that horizontal asymptote. You can see on the edges of the graph, the ends, I am approaching that horizontal asymptote. All right, so let's try part C here. So for the first part of my graph, I want to check for holes. So I'm going to factor the numerator and denominator and see if anything cancels. So on the top, I want two numbers that multiply to -6 and add up to +1. And in the denominator, I have a difference of squares, so x plus 2 and x minus 2. And once I've got it factored, I can cancel common factors. And I can see here that I have a hole at x equals 2. So to find the height of that hole, what I can do is just plug 2 into the resulting function. So for the rest of the question, I'm going to be using this canceled version of my equation. And so I'm plugging 2 in there. And I see that the height of the hole is going to be at 5/4. So I'm going to add that hole to the graph once I get down to that part. So now I'm going to move on to the asymptotes. First up is the vertical asymptote. I'm considering asymptotes in this question because it is a rational function. And again, I'm only looking now at this leftovers after I canceled the hole. I'm not going back and considering the original function. When I look at this leftover piece here, I have one denominator, so I'm looking for where does that denominator equal 0, and our vertical asymptote is at x equals -2. So I want to know what's going on either side of that vertical line. So I'm going to investigate the limit as x approaches 2 from the left of f at x, and then I'll also do coming from the right. All right, so as I come in from the left of 2, -2, I'm going to be plugging -2. I can plug it into the numerator. That doesn't bother me at all, so -2 plus 3 over. And then when I plug -2 but slightly to the left into the denominator, I'm going to come out really close to 0, but again slightly to the left. And then I can simplify the numerator. I get +1 now over almost 0, but a little bit negative. So I have a positive divided by a negative, and when I divide by almost 0, I get infinity. Now coming into -2 from the positive side, again, I can plug -2 into the numerator, no problem. And then when I plug -2 a little bit positive into the denominator, I'm going to get really close to 0, but slightly positive. And then simplifying the numerator, I'm going to get +1. And so I have a positive divided by a positive, that's positive, and dividing by almost 0, I get infinity. And so again, you could be like picturing kind of what's going to happen here. I've got my vertical asymptote at -2. On the left, I'm heading to -infinity, and on the right, I'm heading up to positive infinity. So I'm kind of keeping that in the back of my mind for later on when I do a proper sketch. Next up, we'll take a look for the horizontal asymptote. So I'm going to look at what's the limit as x approaches infinity. So I'm going to use positive infinity first, and then we'll see if I need to investigate negative infinity, or maybe I can just use that similarly trick. So again, I'm using the simplified version of my f at x function. In order to take the limit as x approaches infinity, though, I'm going to factor out the highest exponent on x from the numerator and from the denominator. When I do this, the x's are going to cancel. And now when I take the limit as x approaches infinity, 1 is just 1. And when I plug infinity into this denominator, that's going to get really close to 0. And same thing in the denominator, 1 plus 0. So I get a horizontal asymptote of y equals 1. I am going to just think about, well, how would this change if I were to put a negative infinity in here? And this would become a negative infinity. And I might be thinking of this now as subtracting 0 or subtracting 0, but really I'm still going to get 1. I'll write similarly. Instead of redoing the entire calculation, this is always almost always going to work out for you that you can just write this similarly statement. Especially in this high school class, right? Maybe not in future courses. Okay, so we've got the equation of our horizontal asymptote. I might use my trick from advanced functions to make sure that that makes sense with the trick. Dividing these coefficients in front of the x's, I get 1 divided by 1, which is just 1. Okay, so if I have a horizontal asymptote, I definitely don't have an oblique asymptote, so I'm going to move on to the next step in my algorithm is looking at the intercepts. So to find the x-intercept, I'm going to set y equal to 0. Again, dealing with my simplified version of my function, I'm going to bring the denominator up to the other side and multiply it by 0. 0 times that bracket will equal 0. And then solving for x, I find that there's an x-intercept at negative 3. For my y-intercept, I'll set x equal to 0. So subbing 0 into that simplified equation, I'm going to get 3/2. And so I've got my intercepts. Now moving on, I'm going to look for my maximums and my minimums. Wrapped up in that, I'm also going to be looking for the intervals of increase and decrease. It's going to come from the same chart. So in order to do this, I'm going to need to take the derivative. So you might just want to keep in mind from above that f at x is now x plus 3 over x plus 2. That's the simplified version that I'm taking the derivative of. Maybe you can still see it on your paper. I'm just jotting it down so I can go. I've got a quotient rule here, so I've got a u over a v. So thinking about the quotient rule, I'm going to take the derivative of the numerator, multiply it by the denominator, subtract the numerator times the derivative of the denominator, and then squaring the old denominator. And so when I simplify this, I'm going to get, I'm just distributing that negative through that bracket, and then collecting like terms, the x's actually cancel away, and I'm just left with negative 1 over. Okay, so to find our critical numbers, we want to know where does this thing equal 0. And when I look at this, I've got a fraction here, and I want to know when the fraction equals 0. So really I want to know when the numerator is equal to 0. Well, that numerator, negative 1, is never going to equal 0. So I'm going to say that f prime at x equals 0 has no solutions. And again, that's because the numerator will never equal 0. And then I'm going to think about where does f prime at x not exist. So f prime at x does not exist when the denominator equals 0. So I'm going to take the positive and negative square root of both sides. That's just 0, positive or negative 0. And then I'll bring the 2 over. So I have one restriction here of negative 2. Thinking back to the original function, right here, I see that it's actually a restriction from the original function. And I know that that was our vertical asymptote, right? So this is not actually a critical point. It was just a restriction that I needed to think about. I still need to include all of those restrictions, though, in my table. All right, so let's take a look. Now, I did have another restriction for this function, right, that x cannot equal 2. that's the whole, I'm not going to include it as an interval because it's a whole. I know that the behavior heading in on either side is not changing, right? So if I'm coming into a whole, it's going to be increasing on both sides or it's going to be decreasing on both sides. So I don't need to worry about that. Oops. So here I actually don't need to know the value. I just want to know the sign of the first derivative. And then we can talk about the behavior of f of x. So I'm going to pick some value less than -2. I'm going to pick -10, but you could pick -3 or -1,000, whatever you like. I'm plugging it into my first derivative. Here it is. So I'm going to have a negative in the numerator always, and I'm dividing by, when I plug -10 into this bracket, I get a negative, but I'm squaring it. So I've got a positive in the denominator, and so overall this is going to come out to be negative. And then -2, I don't need to pick a test point. I already know that the derivative does not exist at -2. And then picking some number bigger than -2, I'm going to pick 0, but you could pick -1 or 100, whatever you like. Again, the numerator is always negative. And then the denominator, if I plug 0 in here, I'm going to get a +2, and it's being squared. So I've got a negative over a positive, which is a negative. And so what I find here is that my graph is decreasing. So if you're a visual person, maybe you're just going to draw that. It's decreasing in both of these sections. And don't forget that this is a vertical asymptote here in the middle. So you could write vertical asymptote or does not exist as well. And this is going to help me come up with my graph. Now, if the question had asked for you to state the intervals of increase and decrease, then you would need to include these two intervals as intervals of decrease. All right, so I have some information, and you might do a rough sketch before you get started here of kind of what do we know is going on so far. So just a rough sketch before, so I can plan my overall sketch. I've got my vertical asymptote. I've got my intercepts at like -3/2 and -3. I've got my horizontal asymptote at 1. So I'm kind of just thinking about what this looks like. I know that the graph is decreasing the whole time. I don't have, oh, I also have a whole, right? I have a whole at 2 5/4. So heading over to 2 5/4. So I'm getting closer here. I've got that open circle. So on this side of the graph, and I'm thinking about on either side of the vertical asymptote here, on the right of the vertical asymptote, I have 2 points. So I'm going to say that that's enough. But over here on the left, I only have 1 point. I want one more. So this one here was at -3. I'm going to pick one more. So I'm going to figure out what's going on at -2.5. Or maybe I figure out what's going on at -4. Or something like that, so that I can come up with a better point. So at -4, if I plug that in again to my simplified function, I'm going to get -1 over -2, so it comes out to a height of 1/2. And so now I've got that extra point in here, and that's going to help me sketch my curve. So I've got an idea here of what kind of scale I need to see, and I'm going to get my graph going. So again, that sketch is just rough work. I'm just doing it off maybe to a side sheet of paper to kind of sort out my thoughts. All right, so I'm going to choose a scale here. 4. So I'm adding my scale, labeling my axes, arrows on the end of my axes. Okay, I really want to spread out my y values because most of my y values are fractional. So I'm going to make this 1. And so this is a half, and then this would be 3 halves. And that's just going to help me see a little bit more of what's going on here. All right, so let's add our asymptotes in. So my horizontal asymptote is at 1, my vertical asymptote at -2. And then we'll start adding the points that we know about to our graph. I know that I have a y-intercept at 3 halves and an x-intercept at -3. I know that I have a hole at 2 and 5 quarters, so that's going to be right here, right? Each one of these ticks is worth a quarter, so 5 quarters I need to go up 5 ticks. And then I'm going to get closer to my horizontal asymptote as I move to the right, and then over here I'm going to get closer to my vertical asymptote, and then just connecting the dots. There are no maximums or minimums along here, right? That's what we found when we found that the derivative never equaled 0. There are no flat points. And then over when x is -4, I've got a height of 1/2 here. Again, I'm going to get closer to the asymptotes. And there, I'm done my graph. All right, moving on to the next question. We're going to be looking at this equation here now. Again, I'm going to start by looking for holes. So I'm going to be asking myself about factoring this numerator. So looking for 2 numbers that multiply to 4 and add to -3. My only choices here to get to +4, but add up to negatives, would be -2 and -2, or -1 and -4, and neither one of those adds up to -3. So this doesn't factor nicely, so there are no holes. Don't need to worry about that. So moving on to my vertical asymptote. My vertical asymptote comes from where does my denominator equal 0? And so I see that it's at x equals 2. I'm going to consider the limit as x approaches 2 from the negative side, and the limit as x approaches 2 from the positive side. Again, I can't take the limit of nothing, so I have to either rewrite the equation here, or since I have a name for our equation, I'll just write f at x. So I'm going to take the limit right away because I'm coming in slightly to the left of 2, so I'm a little bit smaller than 2. I can plug it right into the numerator. I actually want to know what that value is. So and then when I plug it into the denominator, I'm coming in slightly smaller than 2. So you can think about like something like 1.999999 minus 2. I'm going to get really close to 0, but it's going to be a little bit negative. And then figuring out what the value is on top. I need that value to figure out if it's positive or negative infinity. When I put this all together here, I've got 8 minus 6 plus 2, so that's 4. And so I have a positive divided by a negative. That comes out as a negative. And then a number divided by almost 0 is infinity. Over here, coming into on the positive side, I'm going to come out with the same numerator. So I am going to come up with 4, but this time when I plug into them a little bit to the right, so I'm going to come out to 0 with slightly positive. I'm okay if you skip this substitution step in the second one because it is the same work for the numerator. You do have to show me the denominator though. And so here I've got positive divided by positive, that's positive, and then dividing by almost 0 gives me infinity. All right, so we've got our 2 behaviors on either side. So remember again, we're thinking about here's my vertical asymptote. On the left, I'm going to negative infinity, and on the right, I'm coming up to positive infinity. All right, so next we want our horizontal asymptote. So if I don't look closely at this equation, I'm going to go ahead and do these limits. But what's going to happen here as you take the limit as x approaches infinity of f at x, you're going to do some work here. Well, let's just do it and show. I wouldn't normally expect you to show me this work. What you're going to do is factor out the highest exponent on your in your numerator. And same thing in your denominator. The highest exponent in the denominator is just x. oh, sorry, I didn't take the limit yet. And what's going to happen here is I can cancel out this x. So I'm going to be left with an x. So I'm going to separate this. I've got the limit as x approaches infinity of x times the limit as x approaches infinity of the two brackets being divided. And what's going to happen here is here, as I take the limit as x approaches infinity of x, I'm putting an infinity in there. So that's infinity times, and over here I'm going to get 2 plus, minus 0 plus 0 over 1 minus 0. And so what I end up getting here is 2 times infinity, which is just infinity, which is telling me that as I move to the right-hand side of my graph, the y values are getting bigger. And so this is all I know. It's not approaching a horizontal asymptote. Now, normally I would not expect you to show me this work. And that's because when I look at the equation, I notice that the degree of the numerator is 1 more than the degree of the denominator. And since it's 1 more, I know that there's going to be an oblique asymptote. And so I'm going to go right into the work instead for finding the oblique asymptote. So to find the oblique asymptote, I take the divisor of my equation, or my function, and it's going to become the divisor in my long division. Or again, you are welcome to set up a synthetic division. And then I'm going to multiply this, or sorry, divide this through. So I'm looking for x times what will give me 2x squared. And then I'm going to subtract those terms. That's going to give me positive x. I'll bring down the 2, and then same thing here, x times what will give me x, and it's positive 1. I'll multiply the 1 through the divisor. And then subtracting here, I'm going to get 4. But I don't need to worry about that denominator, or sorry, that remainder. It's going to go to 0. So therefore, I know that the oblique asymptote is just y equals the quotient. All right. For those of you who haven't graphed a line in a while, just a reminder that when I have y equals mx plus b, this is my y-intercept. I'm going to start there on the graph. And then this guy here, the 2, tells me the slope. So I'm going to rise to run 1. Okay, so next we need to figure out the intercept. So now we know, like, we have this oblique asymptote, and before we had our vertical asymptote as well at 2. So now this is kind of what's happening on my graph. I've got these 2 asymptotes. Moving on to intercepts. Okay, so setting my equation equal to 0 to find the x-intercepts, I'm going to bring that denominator up and multiply it, and so I just end up with 0 equals the numerator. And now I'm going to try to factor this. Now earlier we talked about how it doesn't factor nicely, so I could try the quadratic formula. I'm going to just check the discriminant first here. So the discriminant, remember, is the piece of the quadratic formula that I'm square rooting. And I can't square root a negative. So I'm just checking to see what's going to happen here. And you might just do this in your head quickly and then write it down if it is a negative. If you did it in your head and it came out as a positive, you would do the whole quadratic formula. So I've got 9 minus 16 here, which is a negative number. So that tells me that therefore there are no solutions. So I would write this green part down. It is important. So it tells me that there's no x-intercepts on this graph. I'm never going to cross the x-axis. So next we're going to just look for our y-intercept. For that, I'm going to set x equal to 0. And And so I'm going to get 2 over negative 2, which is equal to negative 1. So just thinking again about what my graph looks like, now I know I'm never crossing the x-axis and I have a y-intercept of negative 1. So you're kind of piecing it together with your rough sketch off to the side. Next, we're moving through our maximums and minimums. To do that, I need to take the derivative. So I'm thinking about my equation. I see it here. This is f at x. So when I take the derivative of this, I do have a quotient rule. So I'm thinking about like a u and a v, and I'm going to take the derivative u prime times v minus u v prime all over the denominator squared. And so the derivative of the numerator is just 4x minus 3 times the denominator minus, this time I'm going to leave the numerator alone, and multiply by the derivative of the denominator. We'll put that all over the denominator squared. All right, so we're going to simplify this a little bit. There's no common factor in the numerator, so I am going to expand out and then collect like terms and see if it factors. And then just multiplying that negative through the second bracket. Collecting my like terms. I haven't set the derivative equal to 0 yet, so I can't multiply the denominator over to the other side. It is still there. And I haven't done that because I'm going to set it equal to 0 and I'm going to see when it does not exist. So I need the whole thing. All right, so I see that there's a common factor. And then looking for two numbers that multiply to positive 2 and add up to negative 4. There are no two numbers, so maybe I'll use the quadratic formula, but I'm going to worry about that later since it doesn't factor. So I want to know two different things. I want to know when does f prime at x equals 0. So we'll work our way through that. But then I also want to know when does the derivative not exist. So for finding where it equals 0, I'm basically asking where does the denominator equal, or sorry, the numerator equal 0. I can divide out the 2 on both sides. So you can be thinking about the 2 moved over here. But I still have 0, and so now I'm going to try to factor this. We already decided that this guy does not factor nicely. If you check the discriminant quickly on your calculator, you're going to find that it is a positive number, so that tells me I do have to use the quadratic formula here. So x is equal to, I'm just going to write it down once in case you've forgotten, but I don't expect you to write this out. You can go right to substituting in. Okay, so negative b is going to be a positive 4. And when I simplify what's under the root there, I get the square root of 8. And then from there, I can simplify, or I can come up with the 2 decimals. So simplifying this, because I have an addition in the numerator, I can split this up and say that it's 4 divided by 2 plus or minus the square root of 8 divided by 2. Now the square root of 8 I can simplify. It's the square root of 4 times 2. Which is the same thing. If I square root 4, that's 2. So just going back to simplifying our radicals from grade 11. And then I can cancel out those 2's, and I'm left with 2 plus or minus root 2. Now, I'm going to want to use these values to sketch a graph. So I am going to change these to decimals. So I'm going to type it in once with the subtraction and once with the addition. All right, coming back up, I didn't finish up here. F prime at x does not exist when, now I'm looking at when does the denominator equal 0. So I'm square rooting both sides, plus or minus, but it's 0, so it doesn't matter. And then I get x is equal to 2. Now I'm going to consider that number and ask myself, does it actually exist on the function? And it doesn't. This is actually a vertical asymptote. It's not a vertical tangent. But these guys here have flat tangents or horizontal tangents. So they might be maximums or minimums. We're going to set up our chart. I'm still including the vertical asymptote in my chart. Okay, we're going to pick a test point. We'll find the sign of the derivative. And then we'll look at what's going on with f of x. So I know that those two values gave me 0 with my derivative, and 2 did not exist on my derivative. On the actual graph, 2 is a vertical asymptote, and I know that these guys are going to be flat. I'm wondering if they're maximums or minimums. Okay, so picking a number between negative infinity and 0.6, you're probably going to pick 0, but you could pick a negative number. I'm going to plug that into my derivative. So I'm heading back up and I'm looking at the most simplified version of my derivative that I have, and here it is. And I'm thinking about plugging 0 into this. In the numerator, I'm going to get 2 times 2, so that's positive. And then in the denominator, I'm going to get a negative squared. And so altogether, that's going to be positive, which tells me that the graph is heading up or increasing. All right, picking a number between 0.6 and 2, you'll probably pick 1. Again, I'm going to scroll back up, looking at my derivative, thinking about putting the value of 1 in here. So I'm going to get 1 minus 1 plus 2. So again, in the numerator, I'm going to end up with 2 times 2 is positive 4. And then plugging 1 into the denominator, I'm going to get a negative squared. Sorry, I I was treating this as if it was a 1 here, but it's a 4. We're going to get 1 minus 4 plus 2, which is a negative number. So we get 2 times a negative is a negative up top. And then in the denominator, a negative squared. So overall here, I'm going to end up with a negative. And that tells me that my graph is heading down or decreasing. So right away I see here I've got a sign switch at my first critical number, so I do have a maximum at this point because it went from positive to negative. All right, next going from 2 to 3.4, I'm going to pick 3. Going back up to my derivative, plug it in here, I'm going to get 9 minus 12. So that's negative 3 plus 2. That's a negative number. So in the numerator, I get positive 2 times a negative. That gives me a negative in the numerator. And then in the denominator, I'm going to get 3 minus 2. That's a positive number being squared. Overall, that's a negative. So on both sides of the vertical asymptote, the graph is decreasing. I'm then picking a number bigger than 3.4. Maybe I pick like 10. Doesn't really matter. I'm going to plug that into the numerator. And in the bracket, I'm going to get 100 minus 40. Plus 2. That's a positive number. So the numerator is positive, and then plugging 10 into the denominator, I'm going to get 8 squared. So that's a positive as well, or a positive squared. And so overall, I get a positive answer. That tells me the graph here is increasing. And so again, at this second critical number, I see that I switch sign from negative to positive. That tells me that there is, in fact, a minimum at that point. Okay, so these values here, I did go off to the side and calculate those by plugging them into my original function. So I plugged 0.6 into the original and I got negative 0.07, and I plugged 3.4 into my equation and I got 10.07 or 10.7. All right, so we're going to draw a quick sketch of what this looks like. Okay, so I'm just going to redraw my quick sketch off to the side so that I get all the good parts on the graph here. I know that I have a oblique asymptote, I have a vertical asymptote, I've got a y-intercept at -1, and so I'm just trying to plan out my scale a little bit here. I have some important points at 3.4 and 0.6. So I know I need to see a lot of stuff going on over here. So I'm going to move my axis a little bit to the left. Okay, heading up, I'm going to count actually 1 square is 1. I know when I look at this graph that I'm missing some important information. So I've got, I need to get up to 10.7 over here. So I need to be able to see above 10.7 for at least 11. All right, so the first thing I'm going to add here is my vertical asymptote. And then next, thinking about adding my oblique asymptote, remember that the equation was 2x plus 1. So I'm going to start at 1, and from there I'm going to rise 2 and run 1. Now my scale, that's actually 2 squares by 2 squares. And so I'm just putting a couple of dots here, and that's going to help me draw this oblique asymptote. Okay, so now we'll start adding some of our points. Again, I've got my y-intercept here at -1, and I know that when I go over to x is 0.6, so I'm thinking about like right here, I'm going to have a height of -0.07. So I've got a point here, and that's a maximum point, remember. So I'm going to see that the graph is going to approach the oblique asymptote over here, hit that maximum, and then start to approach the vertical asymptote. On the right of x equals 2, I have a minimum point at 3.4, so about here, and 10.7. So about here, that's my minimum point. I'd like to have one more point in this region, so I'm going to go back to my equation, and I'm going to pick just a value in here. So perhaps I pick what's happening at x equals 3, and when I plug 3 into my equation, I'm going to get a value of 11. So there's my second point, and from here I'm going to just approach the vertical asymptote and then approach the oblique asymptote. And there's a sketch of my graph. All right, have fun with this homework.